So, in the last lecture I was talking about the Weyl equation. It is a special case for massless fermions, and because the mass equal to 0 allows us to write down equation with one less number of anti-commuting set of matrices, and then you can choose the matrices cleverly enough so that the 4 components can decouple into 2 sets of 2 components, and that produces the Weyl equation with 2 different helicities. Now, before going further, I would like to explain a few more properties of these Vile fermions. Last time I said that this equation is a good description of massless neutrinos which have 2 helicities possible, but in nature we observe only the left handed neutrino and the right handed antineutrino. Now, one can see several other properties of the equation as well from the structure of the anti-commuting matrices which we have used. In particular, in Weyl representation, both the matrices which is gamma 0, which is the transformation for parity, and gamma 2, which is the matrix needed for charge conjugation transformation, are off diagonal matrices. The charge conjugation retains the same structure for the transformation, because just as in the Dirac representation only gamma 2 is a matrix which is imaginary, and since the charge conjugation transforms involved a complex conjugate, only that degree of freedom corresponding to gamma 2 transforming to minus gamma 2 star is important for charge conjugation, and so the transformation matrix remains gamma 2. Now, both these matrices are off diagonal matrices. That means they couple left and R components of the Dirac spinor, or in other words, the parity and charge conjugation cannot act completely on particles of a single helicity. So, for Weyl spinors, P and C are not good operations. In other words, you can't define it for objects of a single helicity. To be more explicit, if I take a left handed neutrino and apply a parity transformation, it produces a right handed neutrino, or equivalently I take a left handed neutrino and apply the charge conjugation transformation, it produces left handed antineutrino. Neither of them actually exist in a pure description of a single helicity Weyl equation. If you want to get a object which is completely defined for a single Weyl equation, one can apply both these operations simultaneously. and since gamma 0 and gamma 2 are off diagonal, the product of the two of them turns out to be a diagonal matrix, and so one can have a combined operation which is commonly referred to as CP, and that produces a right handed antineutrino, and that indeed is a solution of the Weyl equation with an opposite values of energy. So, it turns out that even though C and P cannot be individually defined for Weyl spinor, Cp is a well defined operation for Weyl spinors, which indeed couples the particle and the antiparticle degrees of freedom. There are other consequences also of the charge conjugation symmetry not being defined, or one can also say that these symmetries are violated, that one cannot couple Vile fermions to a interacting field which obeys charge conjugation symmetry, and the important example for such a interaction is the electromagnetic interaction, and the electromagnetic coupling for that reason is something which cannot be properly defined. Because this electromagnetic interaction respects C, or the charge conjugation operation, and in other words the Vile fermions are electromagnetically or under any other interaction which respects charge conjugation, they have to be neutral. They cannot carry that particular charge. One can, on the other hand, have some interaction which violates charge conjugation, and then Vile fermions are allowed to have that interaction, and that is indeed realized in the standard model, where the weak interactions are not charge conjugation symmetric, and they indeed couple to the neutrinos. So, these are called chiral gauge interactions, which is the weak they are allowed for Vile fermions. So, this much about the various kind of interactions Vile fermions can have depending on their properties of parity and charge conjugation. The two component description actually also turns out to be very helpful in discussing various properties of the Dirac fermions as well, and that is possible either where the mass is very small, or equivalently the fermions are highly relativistic. So, the energy is much bigger than mc square, and in that case we can neglect the contribution of the mass, and the Dirac fermions behave as a pair of Vile fermions, and that description is also very helpful in describing how the left handed and the right handed components behave, and one can straight away mention a few properties. One of them is something which is referred to as a chiral charge, leading to a concept of chiral symmetry. It follows from the fact that the operator gamma phi acting on this projection operators for the helicities, it just gives the plus or minus sign of the helicity operator. And so, if one wants to determine the plus or minus, one can measure it just by measuring the expectation value of gamma phi inside the state, and that operator then psi bar gamma phi psi measures the so called chiral charge of the Dirac fermion, and that will essentially tell us whether the particular component we are looking at it contributes as a left handed part or the right hand part. And one can then extend this use of the operator to a sort of symmetry which mixes the two components, and that also can be done again in the case of Dirac fermions, where one can define a transformation which is exponential of I theta gamma phi, where theta is some rotation angle. This is an exact symmetry for massless Dirac fermion, for the simple reason that gamma phi commutes with the matrices alpha. They anti-commute with the matrix beta, but beta is the matrix which drops out in the limit of the mass going to 0. So, under this transformation the equation remains unchanged, and that is called chiral symmetry. It plays a very important role in studying the so called strong interactions, where it is actually broken by a spontaneously generated mass for the Dirac fermion, but that is getting too far ahead into the property of field theory. But it is important that this is a certain symmetry, and if there is a mass term, it will break this particular symmetry, and that is again a useful concept related to the transformations of left-handed and right-handed components. If one write down the contribution of the mass, it rather explicitly appears as a interaction. It couples left-handed and right-handed degrees of and this can be physically understood as saying that if I have a massive particle, I can boost to a frame which is moving faster than the particle. In that frame, the momentum will get reversed, but its spin will remain unchanged, and so the helicity will change sign and it will transform a left-handed particle into a right-handed particle. Such a transformation is not possible if the mass is exactly 0. So, a non-zero mass indeed ends up coupling the left and right components, and that is a way to understand the breaking of chiral symmetry, which is produced by a mass term. The mass term may be explicitly present in the Dirac equation, or it can be dynamically generated as in the case of strong interaction. So, these are the various properties of Weyl equation, and one can look at the clever choice made by choosing a particular set of anticommuting matrices as a transformation on the basis of the gamma matrices satisfying the Clifford algebra. So, the Weyl and Dirac representations are related by a unitary transformation of the Clifford algebra and if one requires, it can be easily constructed. So, then one can use that transformation to relate not just the basis matrices, but any arbitrary components of the spinors. How do you go from one basis to another? So, this is one aspect of the convenience in choosing the basis of Clifford algebra, and it allows you to basically have the degrees of freedom of the Dirac equation when the particle has no mass. There is another transformation again corresponding to a clever choice of the basis of the Clifford algebra that is possible, and which also ends up having the degrees of freedom of the Dirac spinor, and that is what I want to describe next, and that representation is called Majorana representation. And the objects which follow this particular structure, they are referred to as Marana Fermions. This Majorana is an Italian name, and the letter J which is appearing in here in Latin, it is actually pronounced as ya, and that is how I am referring to the name. And what Majorana cleverly observed is that one can rewrite or rather choose a form of gamma matrices, so that the Dirac equation, instead of having complex numbers, becomes completely real. And this is a clever choice which is possible for the relativistic equation. Such a choice actually is not possible for the Schrodinger equation. There you are forced to introduce complex numbers, but in case of Dirac equation, this is a clever trick. So, this is a choice where all gamma matrices are imaginary and the Dirac equation becomes real, which means half the number of degrees of freedom. And it is very easy to see by just again simple permutations on the various matrices which you have already used, and I will write down the representation which was defined by Majorana, and the Majorana matrices I am going to denote by a symbol hat on top of the object. So, alpha 1 hat is defined as minus alpha 1, alpha 2 hat is equal to beta, alpha 3 hat is equal to minus alpha 3, and beta hat is equal to alpha 2, and this implies that gamma mu hat star is equal to minus gamma mu hat, because beta is already one of the gamma matrices, it is imaginary, and other ones which are products of beta and alpha, all the alphas are real, and so alpha times beta, which are the spatial gamma matrices, also are imaginary. And so, one can now use this definition to rewrite the Dirac equation without any complex numbers or the unit I, and that structure looks like h cross del by del t plus h cross c alpha hat dotted with gradient plus I times beta hat m c square psi is equal to 0, and I has been multiplied throughout, and I times beta hat is real, and so are all the coefficients in front. And so, this will have solution psi, which also can be completely real, and then it will have only half the number of degrees of freedom compared to a full complex solution. So, one can have this as a mathematical possibility. The question is, what are the physical properties of such a fermion, and that now one can try to infer from this quantity. The parity transformation can still be defined, it will be still defined by the matrix gamma 0, or in this particular case it will be defined by the matrix beta hat, and there is a a choice available, which is just I times beta hat. There is always a complete freedom in choosing the overall factor of the matrix. If you want to make it real, choose a phase cleverly enough, or otherwise leave it arbitrary, it does not matter. But there is no problem in defining such an operator for the case of Majorana fermion, but for the charge conjugation operation, the relation was a transformation which converted gamma mu star to minus gamma mu, but that operation is already true for the gamma matrices in the Majorana basis. So, the transformation is essentially nothing but identity in the spinor space, and charge conjugation operation then is that psi c is equal to psi star. And if we choose the solution psi to be real, that means the charge conjugated solution is equal to the original solution. That is an unusual case, but it means that the Marana fermions are their own antiparticles. Under charge conjugation, they come back to themselves, and if you are going to interpret the charge conjugation as a object which goes to the antiparticle, which will have an opposite value of the charge, that indeed is not possible in case of Marana fermions. You get the same solution back after applying the charge conjugation operation, and this is an unusual feature. So, the structure now is quite obvious what happened in the Weyl basis and what happened in the Majorana basis. In case of Weyl basis, you reduce the 4 components to 2 components by separating the 2 different values of the helicity or the spin degree of freedom. In case of Majorana representation, we again separated the 4 Dirac components into 2 parts of 2 components each by separating the particle and antiparticle degrees of freedom, and so the spin part will remain inside the 2 component description of a Marana fermion, but there is no separate label for a particle and a antiparticle. Another way to look at it is to introduce the electromagnetic interaction into this Majorana structure of the Dirac equations. So, electromagnetic interactions which are introduced by taking the operator P and writing P minus A into the equation. The P is I times the gradient, and so one it tries to redefine the gradient by this particular transformation. It happens that one introduces back an imaginary operator which was carefully avoided in the other terms of the equation. So, if one wants to stick with the structure that I will only work with a real equation and real operators, it is not possible to introduce electromagnetic interaction, So, Marana fermions are therefore completely neutral. They cannot have any interaction of this p going to p minus a type, and that includes both electromagnetic type interactions and also the chiral type of interactions which are possible in the case of weak interactions. None of them exist because all of them will convert this gradient operator to an extra term which is imaginary, and if you want to stick with the real basis, one has to stick to a object which is completely neutral. It does not carry charge under any type of interaction whatsoever, and this is a rather strict constraint, and it also makes Marana fermions be very hard to detect, because if they are not going to carry any charge, then how are you going to observe them? They can be only observed through their space time effect, because the Marana fermions will carry spin even though they do not carry charge. And that is again leads to a possibility that maybe the neutrinos are Marana particles. So, neutrinos can be Marana not strictly Marana particles, because they do have weak interactions. So, more correctly a mixture of Weyl and Majorana particles. That is again possible by choosing a basis which is slightly rotated away from the Weyl basis in the direction which points towards Marana fermions, and this remains an intriguing possibility that maybe there is some property of neutrino which has Marana characters, and the only property which will display this Marana character is this identity between particle and antiparticle. If so, there will be so called neutrino-less double beta decay possible, and this is the only clinching test which one can make to demonstrate a Majorana character of the neutrinos, that normally a double beta decay will be one beta decay followed by another, in which case first one will emit a neutrino, the second will again emit a neutrino. But if the neutrinos have Majorana character, it will allow a possibility where the two neutrinos can mutually annihilate and disappear into vacuum, and in that case there will not be any neutrino seen at all, and that is what is referred to as a neutrinos less double beta decay, and this is a unique property which will give an unambiguous signature that neutrino has a Majorana character or not. At present there have been lot of investment and efforts to study this particular property, but the question is not yet answered. People have observed double beta decays, but always corresponding to emission of 2 neutrinos. The search for neutrino less double beta decay is on. But barring that reaction, one can allow for a theoretical possibility that one has a Majorana component into the neutrinos, and that can be included in the Dirac equation by this mass term, which is quite a different possibility compared to the Dirac mass term. The Dirac mass term couples the left-handed and the right-handed neutrino modes, while the so called Majorana mass term, which appears in the Majorana equation, it will associate itself with coupling the particle and the antiparticle degrees of freedom. So, this is a different character, and in theoretical models both these kinds of mass terms are investigated, whether the neutrinos has a Dirac mass or it has a Majorana mass, and that question is important because of the observation of neutrino mixing says that one must have coupling between the different components of the neutrino wave function. They can have Dirac or Majorana or both mass terms, and the models having these particular properties have been constructed and they are under investigation in trying to figure out what the predictions are and what kind of parameters will obey the experimentally observed consequences. So, this is a particular feature that Marana fermions are their own antiparticles, and that leads to it peculiar effects. It also leads to a feature that one can have a rather peculiar looking fermion statistics compared to the usual exclusion principle in case of Majorana fermions. But let me first just say that Majorana fermions have this probability density or current that is perfectly fine. But no charge density or current. On top of that, the numbers of the Majorana fermion is conserved only modulo 2, because 2 Majorana fermions can annihilate into the vacuum, or they can be pair produced from the vacuum, just like a particle antiparticle pair. Here the particle and the antiparticle are identified with each other, and the statistic which follows from this kind of rule is rather peculiar. The fermion statistics then obeys this a peculiar rule that if I define a C as an operator which creates a particle acting on the state 0, then the second application of the same operator can take you back to the original state, or equivalently C square is the identity operator. This is different than the exclusion principle, where fermion operator acting on the vacuum state, it will create a 1 fermion state, but if I apply a second fermion operator, it will produce the number 0. It will annihilate the state completely, not produce the 0 fermion state. So, this is different from the exclusion principle, and that is a effect that the number in this statistics is only conserved modulo 2. It does not have the more standard rule of Pauli exclusion principle, where the number can be either 0 or 1, but no other values. So, this is a different sort of story, and roughly this operator behaves as A plus a dagger of the operators of Fermi-Dirac statistics, and this particular superposition that you have both A and A dagger combined together is again manifestation that there is no distinction between a particle and a antiparticle. So, this is the feature of Marana fermion, which appears as a statistics in a many body theory. It is again little bit unusual, and one can ask whether these two different properties of reducing the degrees of freedom of Dirac equation, are they mutually compatible or not, and it turns out that in some situations which depend on the number of dimensions of the space in which one is working, the two properties can be compatible, and in some cases they are different. So, depending on dimensionality, one might even have a situation where the fermions can be defined so that they have both Majorana and Weyl properties simultaneously. So, whether or not Weyl plus Majorana properties can be obeyed simultaneously, that depends on the dimension of the theory, but in our usual case 3 plus 1 dimensions, it is not possible. It is actually possible in a little bit of a simplistic scenario of 1 plus 1 dimension, where the matrices are the Pauli matrices, and one can play around with trying to impose both these conditions simultaneously, and it works out. But I would leave that as an exercise to be explored without going into further details. So, this is a consequence of playing around with the basis of Clifford algebra, and one can indeed find new features, as you have seen. Now, I want to move on to discussion of another kind of symmetry, and that is important together with parity and charge conjugation, and it actually forms a triad of the discrete symmetries important for classification of particles, and that is the concept of time reversal symmetry. Now, this is a symmetry which is difficult to consider in practice, because we know that indeed future and past are very different in our experience. So, there cannot be any symmetry which will equate future with past in any sense, but in mathematical formulation it turns out that many of the equations which we consider for many of the different kind of interactions, they do have this kind of symmetries, and so the equations will not distinguish between past and future in a straightforward fashion, and then one can indeed define a transformation which flips the arrow of time. A simple example is the Newton's second law, where the second derivative with respect to time, which is the acceleration, is related to the force, and if you change the arrow of time, the second derivative with two flips of sign actually does not change its value. So, the Newton's second law is symmetric with respect to this time reversal symmetry, and such considerations also exist in relativistic theories, and we want to study that particular situation a little bit in detail. So, this is a transformation it reverses the arrow of time. And it can be a symmetry for some particular problem, and as I said, e.g. m x double dot is equal to force in case of Newton's equation of motion. But now, let us define this particular transformation more accurately, in the case of quantum mechanics, and there we will define a general rule of what is a transformation which can be associated with a symmetry in quantum mechanics, and that is a analysis which is associated with the name of Wigner, and he gave a very general theorem which listed explicitly what are the possibilities of various kind of symmetries in quantum mechanics, and the condition which one requires for the quantum theory to be symmetric is all the observables do not change under the symmetry transformations, and in quantum mechanics all the observables are the absolute squares of all the transition amplitudes one can construct, and that condition is very simply formulated as a condition between overlap of various kind of states which exist in the theory, and that can be written as overlap of phi and psi mod square in one particular basis will be the same after you have changed the basis according to the symmetry transformation. And Wigner's classification basically listed all the things that can allow such a invariant of the transition probabilities. So, in general Wigner showed that any such transformation falls into two distinct possibility. One of them is called unitary and linear, which means that phi prime is a unitary matrix acting on phi, and it can be summarized as u phi u psi is equal to phi psi. This is the condition of a unitary transformation, and the linearity means is that A acting on psi 1 plus psi 2 is the same as A times u psi 1 plus u times u psi 2, and most of the transformations which we have considered so far fall into this particular category. The translation, rotation, etc., they all correspond to changing a basis by certain unitarity transformation, but Wigner showed that there is a second possibility also available, and that is called anti-unitary and antilinear, and that is a little bit unusual situation where you have the change which not only applies a unitary transformation, but it also flips the amplitude to its complex conjugate, and this is the transformation which Wigner labeled as anti-unitary, and antilinearity is a property which goes along with this transformation, where the coefficients becomes complex conjugate. And based on this general classification, we will discuss time reversal next time.